All right, this is it. This is the wrap-up lecture for Chapter 14, which we will use to try and, polish off the concept of aromaticity. So, aromaticity, we said, makes a molecule extra stable. I'm going to pick up right where I left off on the last mini lecture and show the Frost circle and MO energy diagram, this straight out of your textbook, for benzene. So just to review, what we're looking at again are 6 p atomic orbitals, so therefore we have to have 6 molecular orbitals, and those 6 molecular orbitals are shown right here, and right here in the middle is the Frost circle and the indicated 6 molecular orbitals, or at least their energy levels. So here's the energy increasing bottom to top. Now, it's easy to tell that this guy is the lowest energy, fully bonding molecular orbital. Okay, because clearly all of the nodes are of the same phase, they have complete overlap. We just have the one node right there. And again, it's always really easy to get the fully anti-bonding molecular orbital because we've got nodes aplenty. We've got the planar node and then all these nodes in between all of the p orbitals. I can't even draw it, there's so darn many nodes. I'll tell you what, these other 4 molecular orbitals, it's not intuitively obvious how those are formed. It's just like we had with the psi 2 of the allyl cation. You've got this weird thing happening where you actually like just lose your orbitals. You have this funky nodal plane right in the middle of things, and that's because quantum mechanics says we have to be symmetrical and we have to increase the number of nodes. So we've got 1 node and then we've got 2 nodes and so on and so forth. So look at these molecular orbitals, see how the number of nodes increases, see how the number of antibonding interactions increases, and kind of rationalize their energy levels and why, say, for example, this particular molecular orbital would be of higher energy than this one. That's all I would expect you to be able to get out of this kind of diagram. Like I said, you'll have fun. If you go into PChem, you'll have fun playing with Schrodinger's equation and understanding this in gory detail later. All right, so let's look at one more thing in some gory detail, and that is in these rules for aromaticity, the magic number, molecule has to be planar, molecule has to be cyclic, molecule has to be conjugated. What is this emphasis on planarity? What does planarity have to do with it? Well, the classic way to explain this is to look at the molecule 10-annuline, which is shown here. And the only way I can explain this is by showing you a model. So, here we go. Okay, I'm going to talk to you a little bit about annuline here today to help you understand some of the complexities of aromaticity. All right, so good grief, here's annuline. Obviously, it seems to fit all the criteria for an aromatic molecule. It clearly has 2, 4, 6, 8, 10, the magic number of electrons, obviously cyclic, obviously planar. So what's the problem? Well, the problem is right here in the middle. What you may or may not be able to see is that these little hydrogens here, hydrogen 1 and hydrogen 2, hey, minor detail here, they are trying to occupy the same space. Okay, that is impossible. I can't have 2 hydrogens overlapping here. That's impossible. They can't both occupy the exact same volume. So what I have to do here in order to make this work is I have to twist these things so that the ring obviously is no longer planar. And what you can see here is when I do that, well, I hope you can see this, my two p orbitals, my two adjacent p orbitals right here, they're totally skewed so that they can no longer overlap. So I don't really have conjugation anymore because they can't overlap. So here again is the lack of planarity in my aniline because these two hydrogen atoms are sticking into each other right here, and they cannot do that. They will bang into each other. Okay, so that is the story with aniline. And just to emphasize how bad line structure is, don't forget that there's a little hydrogen there. There's a little hydrogen there, and that's the whole problem. They can't occupy the same space. All right, I need to just quickly throw in the concept of anti-aromaticity. It's just kind of a nice complement to the concept of aromaticity. So we know aromaticity makes something super stable, and we know that that means they have an odd number of pairs of electrons. It turns out, and this all makes sense if you look at the energy diagrams for the molecular orbitals, an anti-aromatic system would have the wrong number, the non-magic number. It has a number of electrons that makes it especially unstable. Okay, so aromatic compounds are especially stable, anti-aromatic compounds are especially unstable and pretty much difficult, if not impossible, to isolate. The distinction here is the number of electrons, and so if you have a cyclic planar conjugated molecule with an even number of pairs of electrons, it's bad news sister. So something like this looks really good, right? It's cyclic, it's planar, it has a pi system, but it has 4 electrons in that pi system. Cyclobutadiene is extremely, extremely, extremely unstable, and we can only gather evidence for it when it's in some kind of special complexes. So that's kind of the bookend to aromaticity. Super stable, aromatic; super unstable, anti-aromatic. Well, what about heteroatoms, ions, and other weird stuff? That's the latter part of chapter 14. And that's going to kind of be on your own. I will, however, say that you can see those of you who have worked with ferrocene in the ITR class know that this is iron plus 2 with sandwiched, if you will, between 2 negatively charged cyclopentadienyl anions. What? Well, hold on. Here's cyclopentadiene. Turns out that cyclopentadiene has just about the same acidity as water. So it is super, super easy to take a base and deprotonate cyclopentadiene, because that particular conjugate base is, hey, it's cyclic, it's planar, it's conjugated, and it has 2, 4, 6, the right number of electrons to make it aromatic. So that is why we show the cyclopentadienyl anion like this. Totally delocalized, super stable, negatively charged ligand for iron. How about this guy? This is furan. Furan is much like pyrrole, and pyrrole we looked at in the previous mini lecture. So you should decide if this is aromatic, anti-aromatic. What's the story with pyrrole? And then how about woofda? These guys, oh, DNA, RNA, oh my gosh, biological systems are full of these nitrogenous bases. Is this an aromatic compound? Well, it certainly could be if that guy is sp2 hybridized and the lone pair is in the p orbital. So sure, this can definitely be particularly aromatic. And what's better yet is by thinking about the pi system and thinking about the orbitals the electrons are located in, you can understand and explain why the lone pair on this nitrogen is the one that gets protonated in that enzyme or whatever particular system you're looking at. That makes all the difference in the world in terms of how a particular compound or metabolic pathway works. So play with those and see if you can't figure out just how and just why these things are aromatic, anti-aromatic, or whatever. So then, what about this radio operator, World War II? Oh, he was all of a sudden there's incoming enemy fire, and the general was yelling at him to call for help, get on the radio, announce that we need backup. So he said NaCl, NaCl over NaOH, NaCl over NaOH, NaCl over, and this general is like, what is your problem? Well, pretty obvious what he was doing. The base was under assault. Get it? Really, really, really bad chemistry humor. Okay, that's it for chapter 14. Next up, the Diels Alder.